So this demonstration is just to get a sense of how the chain rule works and how things are connected in a composite function. So here we have, some proverb says, the more money we come across, the more problems we see. So the outside function is problems, and it's based on the amount of money we have, and so here's some mathematical relationship. And the amount of money we earn is going to be based on the number of hours. So you can see that as you increase the number of hours you work, you get more money, and which is a function. And then this is inside the dependent variable of which your problems depend on. Okay, so it's kind of a chain of action, and it's basically an embedded function. Okay, which we apply chain rule. So looking at this, you can see that as we change the number of hours, the amount of money changes. Okay, and then you have the amount of problems you have, and obviously it says, as a proverb saying, which you have more money, you work more hours, you get more money, and your problems increase not proportionally, but by the square of how much money you have. You can see that blue line going quicker than this one. So the rate of things changing is different for each one, but they're connected. Okay, and then if we can change the amount of our DH hours, right, we can see that the amount of money, the problems increases proportionally differently than the money. So this is in fact a linear relationship, right? So if we change the hours, our money grows linearly, but this one grows by the square. So it doesn't grow proportionally as such. Okay, but you can see that the main idea is that this is connected to this is connected to this, and so these are embedded functions. Okay, so we can just take a look at the rate of change as well. So we change the hours, right? We can see the amount of change in problems. And the rate that this is changing is affecting this rate, which is also affecting this rate. Okay, so we can freeze that DH and we can change the number of hours, and that this stays proportionally the same just because of the way that function is. But you can see that the change in problems changes depending on how we're changing the hours here. And then again, if we want to change the number of the change in the hours, the actual DH, we can see that the change in the problems again changes not linearly, but by the quadratic. Okay, so we can just start kind of seeing this. This is then, if we move this around, this is our overall derivative, our change in the problems as a function of hours, right? So it's going to be the change in the hours by the change in the money, that rate. Then it's going to be the change in the money and change in hours and that rate. And those two rates multiplied together to get this overall rate. Okay, so this is what the chain rule is. And again, this is not to explain the chain rule, but just to kind of show that there is this chain of relationship. So the rates of change are also connected, and they're connected in this multiplying manner, right? Okay, so we can see here we got the change in our hours, change in overall change in problems, and that's different than this relative change here when we talk about the change in problems with the change in money. Okay, but you can see that they are definitely connected. And so this is kind of the chain rule here, right? We have the change in the problems over the change in the money, and then the change in the money over the change in the hours, which is our relative change between these. Okay, and we can see that those changes multiplied together give us the overall rate of change. And we can see that as we move that around, those things are connected, and those rates actually are numerical. This demonstration actually shows you the numerical values actually work in that multiplying fashion.